Let us look at another example of solving linear programming problems using the Big M method. Food P contains 6 units of vitamin A per gram and 7 units of vitamin B per gram and costs 12 paise per gram. Food Q contains 8 units of vitamin A per gram and 12 units of vitamin B per gram and costs 20 paise per gram. So let us understand this example in little detail. So food P, so P is just a representative of some kind of food. So let's say this is food P. Contains 6 units of vitamin A per gram. So there is 1 gram of food P. Let's say this is 1 gram. Now we know that gram and kilogram are the unit of measure of mass, and 1 kilogram is equal to 1000 grams. Now each gram of food P contains 6 units of vitamin A. Now unit means any unit of measure. It can be 6 milligrams or any other unit. So 6 units, let's say this portion represents 6 units. 6 units is vitamin A and 7 units of vitamin B. So let's say this is 7 units of vitamin B and costs 12 paise per gram. So 1 gram of food P costs 12 paise per gram. Now paise and rupee have the relationship of 1 rupee is equal to 100 paise. Now there is another type of food Q, which contains 8 units of vitamin A per gram. So if we take 1 gram of food Q, then it contains 8 units of vitamin A and 12 units of vitamin B. And it costs 20 paise per gram. Now the daily minimum requirement of vitamin A and vitamin B is 100 units and 120 units. So at the minimum we should take 100 units of vitamin A and 120 units of vitamin B. And we have to find the minimum cost of product mix using the simplex method. So we have to find that to meet this requirement, how much of P and how much of Q should be taken so that the overall cost can be minimized. So let's see how we can solve this using the Big M method. So this is the information that has been provided to us in this example. Each gram of food P contains 6 units of vitamin A, 7 units of vitamin B and costs 12 paise, while each gram of food Q contains 8 units of vitamin A, 12 units of vitamin B and costs 20 paise. We have also been given that the daily minimum requirement of vitamin A is 100 units, whereas the daily minimum requirement of vitamin B is 120 units. And now we have to find out the quantity of P and Q so that the minimum requirements of vitamin A and vitamin B are met, and at the same time the total cost is minimized. Now the first step in solving this problem will be to construct an LP model for the problem. So in this example, we have to find out the quantity of P and Q. So let's consider X1 as the quantity of food P in grams, and X2 as the quantity of food Q in grams. So these two become our decision variables. Next, we have to find out the objective function. So here the objective is to minimize the cost of the product mix. Now for 1 gram of food P, the cost is 12 paise. So for 1 gram, the cost is 12 paise. Now we are considering the quantity of P as X1 in the final product mix. So for X1, how much is the cost? So cross multiplication, let's say this is Y, and we have to find Y. So Y into 1 is Y is equal to 12x1. So 12x1 is the cost of x1 grams of food P. And now moving to Q, so each gram of Q costs 20 paise. So for 1 gram of Q, the cost is 20 paise. Now we have considered the quantity of food Q in the final product mix as x2 grams. So for x2 grams, how much is the cost? Let's say this is y1, and we have to find y1. So cross multiplication, y1 into 1 is y1 is equal to 20 into x2. So the total cost in the product mix for x1 grams of food P is 12x1, while the total cost of x2 grams of food Q is 20x2. And this becomes the total cost of the product mix. And our objective is to minimize this cost. So this becomes our objective function. Now let's move to the constraints. Now the first constraint given to us is that the total quantity of vitamin A in the final product mix should be greater than or equal to 100 units. This is because the example says that the daily minimum requirement of vitamin A is 100 units. So that means the quantity of vitamin A in P and Q in totality should be equal to or greater than 100 units. Now 1 gram of food P contains 6 units of vitamin A. So 1 gram contains 6 units of vitamin A. And we are considering x1 grams of food P in the final product mix. So for x1 grams, how much is the vitamin A? Again, cross multiplication. Let's say this is y. So y into 1 is y is equal to 6x1. Similarly, 1 gram of food Q contains 8 units of vitamin A. So x2 grams of food Q will contain how many? So 1 gram contains 8 units. So x2 will contain how many? Let's say this is y1. Cross multiplication. Y1 is equal to 8x2. So the total vitamin A in x1 quantity of P and x2 quantity of Q will be 6x1 plus 8x2. So 6x1 plus 8x2. And this should be minimum 100 units. That means it can be equal to 100 units or greater than 100 units. So greater than or equal to 100. Similarly, for vitamin B, the minimum requirement is 120 units. Now each gram of food P contains 7 units of vitamin B. So x1 grams of food P will contain how much? So that becomes 7x1. So 7x1 plus, now each gram of food Q contains 12 units of vitamin B. So x2 grams of food Q will contain 12 times x2. So 12x2, and this should be greater than or equal to 120. And also one of the constraints is that the decision variables x1 and x2 should be greater than or equal to 0. So this becomes our LP model. We have x1 and x2 as the decision variables. We have the objective function to minimize C, and we have these two constraints. Now before we move to the next step, we have to make sure that the two conditions are met. The first one being that the right hand side of each of the constraints should be non-negative. So here we have the right hand side as non-negative, so that is met. And the second condition being that each of the decision variables of the problem should be non-negative. So that is also met here. So with this we can move to the next step, which is standardization of the problem. Now in order to standardize this problem, our constraints have greater than or equal to sign. So on the left hand side we have to reduce the surplus by subtracting variable s1 and s2. So our constraints will become 6x1 plus 8x2 minus s1 is equal to 100, and 7x1 plus 12x2 minus s2 is equal to 120, and the variables should be greater than or equal to 0. So x1, x2, s1, s2 should be greater than or equal to 0. Now as we know that in the subsequent steps, once we try to establish the basic initial feasible solution, x1 and x2 will become zeros, and then we'll have s1 is equal to minus 100 and s2 is equal to minus 120, which is in violation of this constraint. So let's introduce artificial variables in these two equations, and in order to find the basic initial feasible solution, we'll consider s1 and s2 also equal to 0. So adding artificial variables. So we get 6x1 plus 8x2 minus s1 plus a1 is equal to 100, and 7x1 plus 12x2 minus s2 plus a2 is equal to 120, and x1, x2, s1, s2, a1, a2 are greater than or equal to 0. Now, since we have introduced these new variables in the constraints, we need to add them to the objective function as well. So let's rewrite our objective function. So C is equal to 12x1 plus 20x2 will remain as it is. So 12x1 plus 20x2. Now we'll consider that S1 and S2 have no impact on the cost. So we'll have these two variables with 0 coefficients. So plus 0s1 plus 0s2 plus. Now for a1 and a2, we also need to add a1 and a2 in the objective function. However, we don't want a1 and a2 to appear in the final solution because a1 and a2 are artificial variables which do not have any meaning per se. These are only added in order to get the initial feasible solution. So, in order to make sure that a1 and a2 do not appear in the final solution, what do we need to do? Now, the objective function is based on cost and we have to minimize the cost. So, we need to assign this a1 artificial variable and a2 artificial variable a coefficient which has a very high cost. So since it will have a very high cost, during the solution of this problem, it will automatically get eliminated. So let's consider m as the high number which is representing the cost as the coefficient of a1 and a2. So here we have a positive sign because we are saying that m is representing the cost and is a very high number. So if we add this high cost to the overall cost objective, then the high cost elements should be removed from the solution. So we have now completed step 2. Now let's move to step number 3, which is to create the simplex table. Now the first row of the simplex table is called the objective row, represented by Cj. This row represents the profit or cost per unit of each variable in the objective function. So let's note down the coefficients of the variables in the objective function. So 12, 20, 0, 0, m, m. Now the second row of the table indicates the variables in the problem for which the Cj component have been written in the first row. So x1, x2, s1, s2, a1, a2. And below the second row, the coefficients of the variables in the constraints are noted down. So our first constraint is 6x1 plus 8x2 minus s1 plus a1 is equal to 100. So let's note down the coefficients of the variables in the third row. So 6x1 plus 8x2 minus 1 s1 and 0 s2 and 1 a1 and 0 a2. Let's move to the next constraint. 7x1, 12x2, 0s1 minus 1 S2, 0 A1 and 1 A2. Now there are some more columns to be added to this simplex table, which can be added after establishing a basic initial feasible solution. So let's move to the next step, where we will establish the basic initial feasible solution. Now, since we are using the artificial variables, in order to establish a basic initial feasible solution, we will consider x1, x2, s1 and s2 equal to 0. So x1, x2, s1 and s2 equal to 0. So then we'll get a1 equals to 100 and a2 equals to 120. So a1, a2 become our basic variables, which are the non-zero variables. So now we have to add two more columns on the left hand side of the simplex table. So this column is known as the basis column, and this column is the CB column. The basis column represents the basic variables, which is a1 and a2 in our case. So a1, a2, and the CB column represents the coefficients of this basic variable in the objective function. So m and m, and that to plus m. So m, m. And we also need to add another column towards the right hand side of the table. This is represented by B. This is also known as the solution values column. So here the value of A1 and A2 obtained in the basic initial feasible solution is noted down. So A1 is 100 and A2 is 120. So now this is our basic initial feasible solution. Now we'll move to the next step, which is to perform optimality test on this basic initial feasible solution. So after we have established the initial basic feasible solution, we need to check if this is the optimal solution or not. So now two rows need to be added to this simplex table. The first row is known as Zj or Zj. Elements in the Zj row represent the decrease in the value of the objective function, which will result if 1 unit of the variable in the jth column is brought into the solution. Now Zj values for the jth column are obtained by adding the products of the elements under that column with the corresponding CB values. So for x1 column, 6 multiplied by m plus 7 multiplied by m, so that will become 13m. Now for x2 column, 8m plus 12m, so this becomes 12 plus 8, which is 20m. Next is m multiplied by minus 1, which becomes minus m, plus 0 into m, so 0 into m is 0, so this becomes minus m. For S2, 0 into m is 0, so plus m into minus 1, so this is minus m. For A1, m into 1, which is m, plus 0 into m, which is 0. And for A2, m into 0 plus m into 1, which is m. For B, 100m plus 120m, so this becomes 220m. So next we have to add another row called Cj minus Zj or Zj. Now here, as we know, the Cj row values represent the increase in cost if 1 unit of that column is introduced in the solution, while the Zj row represents the decrease in cost if 1 unit of that column is introduced in the solution. So Cj minus Zj value will bring the net change in the cost if 1 unit is introduced in the solution. So 12 minus 13m, 20 minus 20m. Now 0 minus minus m becomes plus m. Again 0 minus minus m becomes plus m. M minus m is 0. M minus m is 0. Now once we have the values for Cj minus Zj row, these values are to be evaluated to determine whether the current solution is optimal or not. So a positive value in the Cj minus Zj row for a minimization objective will indicate the amount by which the cost will increase if a unit of the corresponding variable is introduced in the solution, while a negative value indicates the amount by which the cost will be decreased if a unit of the corresponding variable is introduced in the solution. So here let's evaluate whether these values are positive or negative. So definitely m was considered a big positive number, so definitely these two values are positive. Now here 12 minus 13 into m. So basically 12 is very low as compared to the value of m, considering that m is infinitely large number. So this number is as good as minus 13 times m. Whereas for the x2 column, the number is 20 minus 20m. So being a huge number that m is, this value is as good as considering equal to minus 20m. So both these values for x1 and x2 are negative. The two values for s1 and s2 are positive, and a1 and a2 have 0 values. So now, in case the values are positive or 0, the current solution is optimal. This is because the positive values indicate that if we try to further improve the solution, the cost will increase. And in case any element is negative, then the solution is not optimal and there is scope for further improvement. So in this example, since we have two values which are negative, we definitely have scope for further improvement. So with that evaluation, let's move to the next step, which is to iterate towards optimal solution. Now since this is minimization objective and since we have negative values for the Cj minus Zj row, which indicates that the solution can be improved further, we observe the values of Cj minus Zj for different columns and mark the column with the maximum negative value. So x1 can be considered as minus 13m, whereas x2 can be considered as minus 20m. So definitely minus 20m is more negative than minus 13m. So let's mark x2 column. Now this column becomes our key column and the variable of that column is our entering variable. So x2 is going to enter the solution. Next we have to find the departing variable out of a1 and a2, which will be replaced by x2. So in order to determine which of the variables will be replaced, elements under the column B are divided by the corresponding elements of the key column. These ratios are noted in the column theta. So 100 divided by 8, this becomes 12.5, and 120 divided by 12, this becomes 10. Now the row containing the minimum non-negative ratio is marked. So here 10 is lower than 12.5, so this row becomes our key row, and A2 becomes our departing variable. Now after we have selected the key column and the key row, a revised simplex table providing an improved solution can be developed. First, the incoming variable now replaces the outgoing variable, and the coefficient of the incoming variable in the objective function is entered in the CB column. So let me do that. So x2, and the coefficient of x2 in the objective function is 20. So 20 comes here. Now we know the key column and the key row, and the element at the intersection of key column and key row is marked as the key element. So here 12 is the key element. So now what we have to do is we have to make this key element as 1. So we'll divide all the elements in the key row by the key element, so that key element becomes 1. So for x1 it will become 7 by 12, for x2 it will become 1, s1 will be 0 by 12, which is 0, s2 will be minus 1 by 12, so minus 1 by 12, a1 will be 0, a2 is 1 by 12, and b is 120 by 12, which is 10. Let me rewrite these new numbers. So now let's move to row A1. So for the other rows, the variable and its contribution, that is the CB column element, are reproduced without change. So A1 and M will be as it is. Now for the other elements, basically we have to modify them, considering that we have to make this element in the key column and row A1 as 0. And that we have to do by subtracting a multiple of the reduced key element from the element in the other row. And then the same multiple has to be multiplied by all the reduced elements of the key row and subtracted from the corresponding elements of the target row. So basically for column x2 we have to do 8 minus 1 is the reduced key element, into x is equal to 0, or x is equal to 8. So 8 needs to be multiplied by 1, then this value will become 0. Now let's do the same thing for all the elements. So 6 minus 7 by 12 into 8, because 8 is the value that we got here. So 4 2s are 8, 4 3s are 12, 6 minus 14 by 3, 3 is the LCM, 6 3s are 18, minus 14, so 4 by 3. So this is 4 by 3. Now for S1, 0 into 8 is 0, so this remains as it is, minus 1. For S2, 0 minus 1 by 12 into 8, 4 2s are 8, 4 3s are 12, so minus 2 by 3, which is 2 by 3. So this is 2 by 3. For A1, 0 into 8 is 0, so this remains 1. For A2, 0 minus 1 by 12 into 8, so 0 minus 1 by 12 into 8, so 4 2s are 8, 4 3s are 12, minus 2 by 3. So this is minus 2 by 3. And for B, it will be 100 minus 10 into 8, so 100 minus 80, which is 20. Let me replace this row with the new numbers. So now that we have an improved solution, let's move to step number 7, which is to repeat step number 5 and 6 until we have an optimal solution. So let's perform the optimality test on this solution. So let's first find the zj values. So 4 by 3 multiplied by m plus 7 by 12 multiplied by 20. So 4 by 3m plus 7 by 12 into 20. So 4 3s are 12, 4 5s are 20. So this is 4 by 3m plus 35 by 3, 3 LCM, so 4m plus 35. But I will write it in this form just so it is easier to interpret. So 4 by 3m plus 35 by 3. Now for x2, 0 into m plus 20 into 1, so this is 20. For s1, m into minus 1, which is minus m. For s2, 2 by 3m, so 2 by 3m plus minus 1 by 12 into 20, minus 1 by 12 into 20. So 4 5s are 20, 4 3s are 12, 2 by 3m plus minus minus 5 by 3. So this becomes 2 by 3m minus 5 by 3. For a1, 1 into m, so m, and 0 into 20 is 0. For a2, minus 2 by 3m plus 20 into 1 by 12. So minus 2 by 3m plus 20 into 1 by 12. 4 5s are 20, 4 3s are 12. So minus 2 by 3m plus 5 by 3. Minus 2 by 3m plus 5 by 3. And then for b, 20m plus 20 into 10, which is 200. So 20m plus 200. Now let's find the value of cj minus zj, which is cj values minus the zj values for each column. So for x1, 12 minus 4 by 3m minus 35 by 3. So we'll keep the component with m separate. So 12 minus 35 by 3 minus 4 by 3m. So let's find this value. 3 is the LCM. So 12, 3s are 36, minus 35, minus 4 by 3m. So this becomes 1 by 3 minus 4 by 3m. So 1 by 3 minus 4 by 3m. For x2, 20 minus 20, this is 0. For s1, 0 minus minus m, which is plus m. For s2, 0 minus 2 by 3m minus 5 by 3. So this will become 5 by 3 minus 2 by 3 m. M minus m is 0. M minus this expression, so let's calculate this. M minus 2 by 3 m plus 5 by 3. So m minus, or rather I'll make it as plus, so minus minus plus, so plus 2 by 3 m minus 5 by 3. So let's calculate this m components together. So 3 is the LCM, 3m plus 2m minus 5 by 3. So this is 5m by 3 minus 5 by 3. So 5 by 3m minus 5 by 3. So now let's evaluate the cj minus zj row for any negative values, because if any value is negative, that means that there is scope for further improvement. So here we have 1 by 3 minus 4 by 3m. So I would consider this negative because m is a huge number and 4 by 3 is also bigger than 1 by 3. So this is negative. Now the value for S2 column, I would consider this also negative. The value for A2, I'll consider this positive. Now we have minus 4 by 3m and minus 2 by 3m. So minus 4 by 3m appears to be more negative than minus 2 by 3m because m is a huge number and 4 by 3 is greater than 1, whereas 2 by 3 is less than 1. So let's consider x1 as the key column because this has the maximum negative value. Let me remove this calculation and then we'll go ahead and find the key row. So in order to find the key row, we have to first find the values of theta. So 20 divided by 4 by 3, which is 20 into 3 by 4. 4 5s are 20, this is 15. And then 10 divided by 7 by 12, which is 10 multiplied by 12 by 7. So this is 120 by 7. Now 120 by 7 is 17.1. So out of 15 and 17.1, 15 is smaller. So we will take this as the key row. And so the element at the intersection of key row and key column becomes our key element. So 4 by 3 here is key element. So x1 is now going to be entering the solution and a1 is going to be departing the solution. So x1 will replace a1 in the basis column and the coefficient of x1, that is 12, will replace the CB value. So let's do that. So this will be x1 and the coefficient of x1 is 12, so this will be 12. Now we have to make this key element as 1. So we'll divide the key element by itself, that is 4 by 3, and also we'll divide the key row by the same element, which is 4 by 3. So let's do that. So 4 by 3 divided by 4 by 3, this will become 1. Then 0 divided by 4 by 3 is 0. Minus 1 divided by 4 by 3 becomes minus 3 by 4. 2 by 3 divided by 4 by 3. So 2 by 3 into 3 by 4. So this is 1 by 2. 1 divided by 4 by 3 becomes 3 by 4. Minus 2 by 3 divided by 4 by 3. So minus 2 by 3 into 3 by 4. This is minus 1 by 2. And 20 divided by 4 by 3. So 20 into 3 by 4. 4 5s are 20. This is 15. So let me replace this row with the new values. Now let's move to the row x2. So here we have to make the intersecting element with the key column for row x2 as 0. So this becomes 7 by 12 minus 1 into x is equal to 0, or x is equal to 7 by 12. So 1 into 7 by 12 is 7 by 12, and 7 by 12 minus 7 by 12 becomes 0. Now for column x2, 0 into 7 by 12 is 0, and 1 minus 0 is 1. For column s1, 0 minus 3 by 4 into 7 by 12. So 0 minus 3 by 4 into 7 by 12. 3 1s are 3, 3 4s are 12. So this becomes minus minus plus. So 1 into 7 by 4 into 4. So this becomes 7 by 16. For S2, minus 1 by 12 minus 1 by 2 into 7 by 12. So minus 1 by 12 minus 1 by 2 into 7 by 12. So this becomes minus 1 by 12 minus 7 by 24. So 24 is the LCM. 12 2s are 24, so minus 2 minus 7. So this becomes minus 9 by 24. Now 3 3s are 9 and 3 8s are 24. So this becomes minus 3 by 8. So minus 3 by 8. For A1, 0 minus 3 by 4 into 7 by 12. So 0 minus 3 by 4 into 7 by 12. 3 4s are 12. So minus 7 by 14. minus 4, 7 by 16, sorry. So this is minus 7 by 16. For A2, 1 by 12 minus 1 by 2 into 7 by 12. So 1 by 12 minus 1 by 2 into 7 by 12. So this is 1 by 12 minus plus 7 by 24. So 24 is the LCM. 12 2s are 24 plus 7. This is 9 by 24, 3 by 8. So this is 3 by 8. And for B, so 10 minus 15 into 7 by 12. So 10 minus 15 into 7 by 12. 3 5s are 15, 3 4s are 12. So 10 minus 35 by 4. 4 is the LCM. 40 minus 35. So this is 5 by 4. So this is 5 by 4. Let me replace this row with the new values. Okay, so now that we have an improved solution, let us find the value of Zj. So 12 into 1 plus 20 into 0, which is 12. 12 into 0 plus 20 into 1, which is 20. 12 into minus 3 by 4 plus 20 into 7 by 16. So 12 into minus 3 by 4 plus 20 into 7 by 16. 4 4s are 16, 4 5s are 20, 4 3s are 12, minus 9 plus 35 by 4. So 4 is the LCM. 9 4s are 36, so minus 36 plus 35 minus 1 by 4. So this is minus 1 by 4. 12 into 1 by 2 plus 20 into minus 3 by 8. So 12 into 1 by 2 is 6 plus 20 into minus 3 by 8. 4 5s are 20, 4 2s are 8. 6 minus 15 by 2. 2 is the LCM. So 12 minus 15 minus 3 by 2. So this is minus 3 by 2. For A1, 12 into 3 by 4 plus 20 into minus 7 by 16. So 12 into 3 by 4 plus 20 into minus 7 by 16. So 4 4s are 16, 4 5s are 20, 4 1s are 4, 4 3s are 12. 9 minus, because plus minus minus, 35 by 4. 4 LCM. 36 minus 35. This is 1 by 4. 12 into minus 1 by 2 plus 20 into 3 by 8. So 12 into minus 1 by 2 is minus 6 plus 20 into 3 by 8. So minus 6 plus 4 2s are 8, 4 5s are 20. So 15 by 2. 2 LCM minus 12 plus 15. So this is 3 by 2. Now for column B, 12 into 15 plus 20 into 5 by 4. So 12 into 15 plus 20 into 5 by 4. 4 1s are 4, 4 5s are 20. 12 into 15 is 180 plus 5 5s are 25. So this becomes 205. Now let's find out Cj minus Zj. So 12 minus 12 is 0. 20 minus 20 is 0. 0 minus minus 1 by 4 is 1 by 4. 0 minus minus 3 by 2 is 3 by 2. M minus 1 by 4. M minus 3 by 2. So here 0 and 0 is of course meaning that there is no chance of improvement, because the cost is going to be the same if we introduce any more of these units in the solution. 1 by 4 and 3 by 2 for columns S1 and S2 indicate that if we increase these two, then the cost is going to increase, whereas we want to minimize the cost. And for A1 and A2, we have M minus 1 by 4 and M minus 3 by 2. M being a huge number, These two are also positive, which mean that we cannot reduce the cost by introducing any of these in the solution. And anyways, a1 and a2 we do not want to introduce in the solution. So that means this solution is the optimal solution because there is no negative number in the Cj minus Zj row. So now our solution becomes x1 is 15, x2 is 5 by 4, and the value of C is 205. Let me clean this calculation here. Now x1 was the quantity of food P in grams. So we should have food P equal to 15 grams and food Q equals to 5 by 4 grams, and the total cost is 205 paisa, which is equal to 2.05 rupees. So this is the optimal solution for this problem.